Hello and welcome to seminar number 17. Today we are going to talk about exam questions. So what's the plan for today? Reading the chart of nuclides, decay products, decay series, simple activity calculations and decay equations. As a quick disclaimer, these are not the exact questions of the exam. And even though if you can answer all of them correctly in this presentation, you are not going to pass the exam. You are just going to get 100% on the, first 3 or 4 questions. And they are very easy and beginner friendly, but don't get your hopes up. If you do well on this presentation or the questions on the presentation, you are not going to pass the exam. I'm really sorry, but I wanted to give you a simple introduction into some basic knowledge that one has to have for the exam. So let's get started. Reading the chart of nuclides. You will see a question, something like this. You have an excerpt of the chart of nuclides, and then you have to read based on the colors and other information on the tiles of the chart of nuclides. Does this or that isotope do alpha, beta minus, beta plus electron capture? And as you can see here, I will give you a minute, or you can just pause the video and think for yourself. So the iodine 127 is stable, as we can see by this being black, and it makes up 100% of all iodine isotopes on Earth, naturally occurring, and these ones are radioactive. And now it's the question, which type of radioactivity do they emit, or do they have? Well, looks something like this. If it were to do alpha decay, you would see at least something yellow here, and an alpha energy, which we can't see in both tiles, so they don't do alpha decay, but they do beta minus decay, because you can see these are colored in blue, which stands for beta minus decay, and as we can also see, we have an energy. So the beta particles of this beta minus decay have a maximum energy of 0.9 mega electron volts. Of course, that wasn't a question. It was just a question if it does beta minus decay. And as we can see here, blue and beta minus. So there will be a beta minus decay. And we can also see this is marked in red. Now, red has 2 meanings. So it's either electron capture or electron capture and beta plus. So now, if you can see red, there is of course going to be an electron capture route that the radionuclide can do, but then must not always be a beta plus decay associated with it. If you want to see it, you now have to look at the chart of nuclides in this tile, and if we can see a beta plus sign and some energy, we know that this beta plus decay happens. So as we can see from red, it has to do electron capture, but it can also do beta plus decay because of this beta plus sign here. These were the information that one has to read out of the chart of nuclides. Coming to the next ones, decay products. So here I have the mother nuclides and here the daughter nuclides, and feel free to connect all of them with either 1, 2, 3, and 4 standing for alpha decay, beta minus decay, beta plus, or isomeric transition. And if you did it correctly, it should look something like this. Samarium 146 does alpha decay into neodymium 142. So this connection of the mass difference of 4 should indicate that it does alpha decay. Next one, we can see Promethium 149 does beta minus decay to samarium, and therefore the proton number changes, but the nuclear number doesn't change. So this connection via the same nuclear number should indicate that we have some sort of beta decay. And this is also true for yttrium and strontium. So yttrium 188 does electron capture beta plus to strontium 88. And as we can see here, we have iridium and another iridium isomer. So this iridium 192M does isomeric transition into iridium 192G, which I left out because there's no need for that. Okay, talking about decay series, starting from dysprosium 150 doing alpha decay until we reach a stable isotope. So if you look at the chart of nuclides, we can see that dysprosium 150 does not only do alpha decay, but it can also do electron capture beta plus. But since I'm the quiz master here, I wanted you to go with the flow when it comes to the alpha decay. So it does alpha decay into gadolinium 146, which is a electron capture beta plus nuclide. It decays into europium, which can also do electron capture beta plus to form samarium. And as we can see here by the yellow marking of this tile, it does alpha decay and decays into neodymium 142. Here we can see the decay mode based on the color of the tile. So cluster emission would then be something gray at the top corner. But we were talking about alpha decay and electron capture beta plus. When talking about simple activity calculations. So How much do 5 megabecquerels of pure uranium-238 weigh? For this, you would need the constant specific activity. I like to use this one rather than the decay constant because I think it's a more intuitive approach to this. You can just look up the specific activity if you look at the Isotope Browser app and then search for uranium-238 and it's right at the top. There you can see the specific activity. So we have 5 million becquerel. The specific activity, if looked up in the Isotope Browser app, is 12,433 becquerels per gram. And therefore, these 5 megabecquerels are 402 grams of pure uranium-238. If you want to do these exercises, feel free. So 6 kilobecquerels of carbon-14, 6 kilobecquerels of sulfur-35, 5 milligrams of protactinium-231 and 0.5 milligrams of polonium-210. Then you have to calculate either the weight or the activity of this or that samples. So 6 kilobecquerels of carbon-14 in the calculator shows us something like 3.62 times E minus 8. E minus 8 is 10 to the power of minus 8. This equates to this number of grams or just 36.2 nanograms. If we look at sulfur-35, the same activity has only a weight of 3.79 picograms. This is because carbon-14 has a half-life of 5,000 something years and sulfur of just 90 days. Therefore, it has a much higher specific activity. Therefore, you just need less to have the same activity. This is also the same for protactinium and polonium. You can see that polonium-210 has a much higher activity even if you have just a tenth of the same amount of protactinium-231. But as a quick side note, the activity is not a great indicator when it comes to assessing the danger of a radionuclide. On a activity-to-activity basis, protactinium is more toxic than polonium. This is because it has a much higher biological toxicity. Of course, to get 1 becquerel of protactinium, you would need much more of the substance than for polonium, but on an activity-to-activity basis, protactinium-231 is more dangerous than polonium-210. Coming to decay equations, this is an equation that you might even use in biology because it just explains exponential growth or decay. In our case, it describes the decay due to this minus sign here. So if you want to have some exponential growth, you would just swap this minus sign to a plus sign. So AT equals A0 times E to the power of minus ln2 divided by T1/2 times T. A0 is the initial activity from the get-go. E is just Euler's number. There is a button on the calculator. T1/2 is the half-life. Just look it up. It's literature for every isotope. But I like to convert this into seconds because we are talking about becquerel. It's not really necessary. It's just necessary to keep T1/2 and T in the same unit. But since we talk about becquerel, which is a unit based on decays per second, I just like to use seconds to calculate stuff. It's a bit more intuitive approach, in my opinion. Yeah, T is the time from the get-go to now, converted into seconds because I like to use it in seconds. And ln is also just a button on the calculator. It's the natural logarithm to the basis of Euler's number. As I said before, why seconds? Becquerel is defined as a unit, decay per second, so I like to use seconds as a general unit for this equation. Let's practice that on 3000 becquerels of carbon-14. The T1/2 is 5,700 years. So for any practical calculations, I just use these numbers. Of course, 1 year on average does not have 365 days, but 365.25 days, or even more accurate. But I'd like to keep it simple for now and calculate with these numbers. So a month also has just 30 days, not 30. I just like to keep it simple for now. T, since the time of the get-go, I set to 5,700 years because it makes the calculation a bit easier. And if we look at it, it comes out to 1,500 becquerels, which makes sense because we waited 1 half-life. So the activity decreased to half of what initially was at the beginning. So 3,000 and 1/2 of that is 1,500 becquerels. Now it's your turn. If we bought 37 megabecquerels of sulfur-35, how much activity will there be next semester, so in exactly 6 months? It would look something like this. We have 37 million becquerel and the half-life of sulfur-35 looked up in the Isotope Browser app, converted into seconds, and the 6 months converted also into seconds looks something like this. You get this activity which is still left after 6 months. Congrats if you could follow. all of my equations. If not, go join the Discord server, we can chat there, and I would explain that to you once again, or just feel free to leave a comment down below. And thank you for your attention, goodbye.